Today, we're going to pull back the curtain on the invisible engine that powers, well, pretty much everything you do online. We are diving deep into the world of data structures and algorithms, which is the secret sauce that makes your favorite software feel so incredibly fast. You've totally felt this, right? You tap on one app and boom, it just flies. It's instant, it's snappy, it feels good. And then you open another one and it's like you're walking through mud, you're waiting, tapping your fingers. So what's the deal? What's the real difference? Well, the secret isn't some superpowered hardware or a magical programming trick. It all boils down to one single fundamental idea: organization. Yep, that's it. The speed and the feel of any piece of software comes down to how smartly it arranges and gets to its own information. And that brings us perfectly to our first big idea: data structures. The best way to think about these is like blueprints for building all sorts of digital filing cabinets, where every single one is designed for a very specific job. So a data structure isn't the data itself, right? It's the container you decide to put the data in. Think about it this way. You wouldn't keep your phone numbers in a photo album, would you? Of course not. Picking the right container from the get-go is the first crucial step to building software that feels amazing to use. So, let's look at the most basic building block of them all, the one you'll find in pretty much every single programming language out there: the array. It's basically the digital version of a numbered list or, a row of mailboxes. Simple and straightforward. But here's where we see the first big trade-off. Because an array keeps everything neatly lined up side by side in memory, grabbing, say, item number 5 is unbelievably fast. But what if you need to stick a new item right there between item 2 and 3? Uh-oh. Now you've got to shuffle everything else down the line just to make room. It's super organized, but it can also be really rigid. Okay, so we've got this idea of fast and slow. But those words are kind of subjective, aren't they? In the world of computer science, we need a really precise way to measure performance that works the same no matter what computer you're on. And we do that with something called time complexity. Now, this isn't about counting seconds or minutes. No, it's all about understanding how an operation scales. If I double the amount of data I'm working with, does the time it takes to finish also double? Or does it get 100 times worse? That's the critical question we have to answer. The special language we use to talk about this scaling is called Big O notation. You can think of it as the universal ruler for an algorithm's efficiency. It lets programmers everywhere talk about performance in a standard way, whether they're coding for a massive supercomputer or just a tiny smartwatch. Let's just quickly look at the big ones here. O of 1, or constant time, is the absolute dream. It takes the same amount of time whether you've got 10 items or 10 billion. That's the speed of grabbing an item from an array. O of n, linear time, is also pretty solid. The time just grows in a straight line with the data. But then you get to O of n squared, quadratic time. Oh boy. This is where an app goes from zippy to totally frozen. If you double the data, it takes 4 times as long. This is the danger zone. All right, enough with the theory. Let's actually put this stuff into action and see how choosing the right algorithm can make a night and day difference when you're just trying to find something. So in the left corner, we have linear search. It's simple. You just start at the beginning and check every single thing one by one. This is O of n. But on the right, you have the genius of binary search. Now, its one requirement is that the list has to be sorted first. By jumping to the middle and asking, is my item higher or lower, it chops the number of things to search in half with every single guess. This is the difference between O of n and O of log n, and it is massive. It's like flipping through a messy pile of papers versus looking up a name in a phone book. So speaking of sorted lists, that kind of begs the question, right? How do we get them sorted in the first place? Well, sorting is one of the most classic problems in all of computer science, and there are tons of ways to do it. Some are just much, much smarter than others. So let's start with a real classic slowpoke, bubble sort. It gets its name because the biggest numbers slowly bubble up to the top. It just looks at 2 items at a time, and if they're in the wrong order, it swaps them. Then it does it again and again and again, forever. It's easy to understand, sure, but it is incredibly inefficient. It's a textbook O of n squared algorithm. It gets really bad really fast. There has to be a better way, right? And of course there is. Instead of making a million tiny little swaps, what if we just broke the problem down into smaller, easier pieces? This is a really powerful technique, and it's called divide and conquer. Now, the big brain moment with merge sort is this. A list with only one item in it is, by definition, already sorted. So the algorithm just keeps splitting the list in half over and over until it's just a bunch of tiny lists with one item each. Then it conquers by cleverly merging those little sorted lists back together in the right order. This approach is unbelievably faster, running in what's called O of n log n time. It's how your phone can sort thousands of contacts in the blink of an eye. So we've seen that arrays aren't a one-size-fits-all solution, and that there are way better strategies for doing things like searching and sorting. A great programmer has a whole toolkit full of these different structures, and they know exactly which one to pull out for which job. I mean, you wouldn't use a hammer to turn a screw, right? So you wouldn't use a rigid array for a problem that needs a ton of flexibility. That's when you reach into the toolkit for other things, like stacks and queues. Let's take the stack. Its rule is dead simple. Last in, first out. Think of a stack of plates at a buffet. The last plate you put on top is the first one you're going to take off. This is perfect for something like the undo button in your text editor. The last thing you typed is the first thing that gets undone. Now, the complete opposite of a stack is a queue. It's first in, first out. You know this one. It's just a line at the grocery store. The first person to get in line is the first person to check out. It's perfect for managing things that need to be done in order, like a bunch of print jobs. And then you get into even more complex structures like a tree, which is absolutely perfect for anything that has a hierarchy. Your computer's entire file system, that's a tree. This structure is what lets you click through folders instantly because the computer knows the exact path from the very top, the root, all the way down to your file. They are literally everywhere. So let's just tie this all together. Fast, responsive software doesn't happen by accident. It's the result of very careful, deliberate choices. Big O gives us the language to measure how things will perform, and knowing the right tool for the job, whether it's an array, a tree, or a queue, is what makes that incredible performance possible. And so, I'll just leave you with this little thought. The next time you search for a file and it just appears instantly, or an animation plays on your screen perfectly smooth, just take a second. You're not just looking at clever design, you're actually experiencing the elegance of a well-chosen data structure and an efficient algorithm, that invisible architecture just working perfectly behind the scenes.